All right, quick take on 6.3 here. If I saw this in the homework, what I would think is, okay, 10 to the something equals 10,000. We're talking like basis property here, but really what I would do with something this simple is I would just start talking tens because this is a power of 10. So we'd just be like 10 to the 1 is 10, to the 2 is 100, to the 3 is 1,000, and keep going until you got the number you want, 10,000 in my case. So I would be like 4 of them would get me right where I want to go. 4 tens is 4 zeros, so that's 10,000. So then the end would just be 4 in my case. That's all I would do in something like that. Number 2, use a like basis property to solve this. This one is a little bit more like basis looking. It's hard to tell exactly what numbers to think of, but I know 81, numbers like 9 come to mind. And then maybe if I have to go further down than 9, sometimes, 243 may not be a power of 9. And if not, then I could think of like, well, what's 9 made out of? And it's made out of 3s. So I might just say that 81 is a power of 3 if I can get 243 to work for that. So let's see what we can do with this. Okay. 243. Oh, yes. As a matter of fact, when I'm looking at this, I'm seeing 81 is made out of a bunch of 3s. So if I had the 81 here equals 243 to the n power, I'm thinking 81 is like 3 to the 4th because it's like 9 times 9, which is, 3 times 3 times 3 times 3 because that's 9 times 9, so that's 81. So 81 is 3 to the 4th. That's my little arrow drawing down to 3 to the 4th, whatever. And then 243, I happen to know, is 81 times another 3. So that'll be 3 to the 5th is the 243 part. But notice that 243 is also taken to the n power if we look up here at the n power thing. And so we'll have to say this is 3 to the 5th was the 243 part. And then that is to the n. And so that's a little weird. But whatever. And so what you might remember is that if I have stacked exponents with the 5 and the n going on, that's like distributive. So I might say something like this is 3 to the, and then 5 times n will do. And so 5 times n is just 5n. So we have 3 to the 5n equals 3 to the 4. And by like basis property, the only way these expressions are equal is if their exponents themselves are equal. So we don't need the 3's at that point. We'll just be looking at the 5n equal to the 4, just the exponents at that point. And so we'll say, well, 5n must equal 4, and then I would just divide out the 5 or something and get n equals 4 over 5. In my case, that's what I would do. Okay, more like basis stuff. If I saw this one here on number 3, they both look like powers of 10, so I would maybe start there and say 10,000. Let's see, it's 4 zeros, right? So that would be 10 to the 4. And then equal to this one, 1 over 10. I don't know, it's something to the n power, so I'll put an n there, but 1 out of 10, that's the same thing as 10 to the negative 1 power is what I would say. And then we'll do the same thing like on the last problem. And we'll say negative 1 times n is just negative n or negative 1n, and then equals 4. Because once we get the 10s to match on the bottoms, we don't need them anymore. We'll just be dealing with the exponents themselves. So negative 1n equals 4, and then you solve that out and you get n equals negative 4 or something like that. I'll dot that. And then let's see here. Similar idea. I'm looking at 27 and 243. Looking like another 3 thing. If I saw something like this, I would think something like 27 is like 3 to the 3. And then that's to the x power. And then 1 over 243. Remember, 3 to the 5 is 243. But since it's 1 over 243, we could say that's 3 to the minus 5. And then we'll do that thing where we times these two and then equals the 5, and we don't need the 3's anymore. Something like 3x equals 5 or whatever, and then solve that out. That's what I would do. This next one is best case scenario in a way, like basis property, and they both have the like basis pretty obvious at this point because they both have a base number of 2. So at that point, I would say I won't even need the 2's anymore because of this stuff, and so I'll just say the x plus 1 part is equal to the 2x plus 4 part. And then I'll just solve that equation, get x by itself, move the x over here or something, whatever. 1 equals, what is that, 1x plus 4, and then keep going until you solved it. That's what I would do there. Okay, and then on number 6, similar but different idea, we have a 3, an extra 3 timesing, then times 3 to the n equals 243. A lot of 243 showing up in this version of the homework. Anyway, probably what I would do there is just notice that it's the 3 that's in parentheses that's taken to the n power. This other 3 sitting out there, this other 3 sitting out there to the left, he's just timesing by the exponential expression. So if I were to solve an equation, I'd probably start by dividing that 3 out, so it looks a little bit more like the others, Then this 3 is gone, and now I have just 3 to the n equals whatever 243 divided by 3 is, which I believe is 81. And then from that point, you can really just solve it like you did on number 1 and just figure out how many 3's does it take to make an 81, and that'll be good. Okay, something similar on number 7. It's a lot like what we had done before. Just remember, 1/2 is like, it's a 2 to the 1, but it's downstairs, so it's 2 to the minus 1, and then all of that is to the x plus 1 power. That's kind of sloppy, but whatever. And then equals, and then this is already a power of 2, that's 7x minus 2, and then by the time we got that, we're just doing the same old thing. We're going to distribute this. We'll say we don't need the 2's on the bottom, and then we have negative 1 distributing to the x plus 1 on the left equals 7x minus 2. And then you just distribute that negative 1 and start solving out for x like we do. Now number 8, real similar idea to, I don't remember, number 6 or something, whatever it was like. And so if we have a 4 timesing next to that 10 to the x power, it's the 10 that's being taken to the x power. Now we have an extra 4 floating around and a plus 39 floating around. So we're going to get rid of both of those. Equals 4,039. And then the way that would go is like when we're solving for old-fashioned linear equations, the old 2-step. We have a plus 39, so I'll minus the 39. And then we have, that'll leave us with 4 times 10 to the x equals just 4,000. And then we'll divide the 4 from both sides. And that'll leave us with just 10 to the x here on the left equals whatever 4,000 divided by 4 is. And the diary here over here on the right, we're going to say that'll be a 10 to the x left over equals just 1,000. And now we're just solving it like number 1 again, saying 10 to the something equals 1,000. And figure out how many 10s it takes to get to 1,000 or something. Let's see here. Okay, this is a little bit different. When I look at this on number 9, we have an 8 to some power and a 16 to another power. And we got to figure out a way to make those both work as being, like bases, as we call them. We want the base numbers to match, and they don't quite. And it's tempting to think like, well, 8 goes into 16, so maybe I could turn the 8 into a 16 or the 16 into an 8 times 2 or something. You could be like, well, 16 is just 8 times 2, but it doesn't help us with a like bases approach, because really what I'm hoping to do is describe both 8 and 16 as being a power of some smaller number. And if I were to see this problem doing the homework, what would come to mind for me is 8 is 2 to the third. That's the 8 part. And then I have an x minus 5 there. And then, let's see here, 16 is also a power of 2. That is 2 to the 4th. And then I have that, so that's the 16 part. And that's to the 3x plus 5. That's what I would do. So this is the 8 part, 2 to the 3, that's 8. 2 to the 4 is 16, and now they both look like 2 to the something. And once you got them looking like 2 to the something, we'll say we don't need the 2's anymore. We just do the 3 times the x minus 5. That's 3 times x minus 5 equals, and then this is 4 times of 3x plus 5. And now we're just back to solving equations. we'll distribute this and distribute that and try and get the x by itself like we do. Let's see here. Find the solution to the exponential equation. This is a little bit funny. Now we got an e thing going on. So 17e to the x minus 8 equals 5. One thing about this is we can probably start getting rid of some of the extra stuff, and then we'll have to deal with the fact that there's an e in here. And so we have a minus 8, so we'll plus the 8, and that'll be good. Now I have 17e to the x equals 13. And then we'll divide the 17 out even. That seems to be helpful. That leaves us with just e to the x equals 13 out of 17. And that's a little weird because we don't want to have to figure out e to some power. It makes 13 out of 17. It's not going to go very well. So once you get down to this, guys, we have an exponential equation that's hard to solve. Maybe, and that's certainly not going to go by like a like basis formula thing. Probably what I would do is put it in logarithmic form. So this would be a log base e, because of the base numbers e, log base e of 13 over 17 equals the x now, equals the exponent, which is x. And there, by the time we're there, you got the x by itself. And it's just calculator work. But remember, log base e, if you have a calculator that can handle that, then do that. Otherwise, remember that what's easier is a log base e is a special logarithm. It's a natural log. I'll put it in cursive. That's natural log, or ln, of 13 out of 17. And you just shoot that in the calculator, call it a day. This one says you can write it in terms of logarithms or correct to 4 decimal places. So really, if you wanted to, you could even just write ln of 13 out of 17 right in the answer box if you know how to write that. Just ln, parentheses, 13 out of 17. It should take it. Or else if you want to shoot it into your calculator, you can just make sure you round it off after 4 decimal places. That's what I would do. And blah, blah, blah. Okay, what else? Solving for x here. Now we're into the whole logarithm thing. This is a place where we're just seeing more and more of this situation where a like basis property isn't going to help us out. So 2 to some power equals 35. 2 doesn't even go into 35. It's certainly not a power of 2. And so maybe we'll just take it. If you see an exponent equation that's hard to solve, let's put that into logarithmic form. So this would be a log base 2 of 35 equals x, and then that's something you can just shove into a calculator. Some of them can handle it just like that, or else you can use the change of base formula. If you can't pick your bases in your calculator, anything that does logs will be able to handle this one in one way or another. We'll say that's the same thing as common log of 35 over a common log of 2 by the change of base formula. Here's another way to type that in. And then once again, it says you may enter an exact value. So you could even just write in this, log 35 over log 2, and write into the answer box if you're careful, and it should take it, or else you can round it out to 4 decimal places, and it'll take it that way too. More stuff with solving for weird exponential things. If I saw 4 to the 4x minus 3 equals 40, I might suggest that one we could do we'll try it out in logarithmic form as well. So that would be like log base 4 of 40. Of 40 equals 4x minus 3, because that's the exponent part. And then this is the thing where, you probably shove it into a calculator, either like it is, or you could do it as log 40 over a common log of 4, and that's fine as well. And then we got to get this x by itself. And so let's see here. To get rid of that minus 3, we'll plus the 3, Then we have all that log expression plus 3. So we have log 40 over log 3. And then we'll plus 3 at the end of it. That equals 4x. And so then dividing that 4 out, now we'll have all of that mess divided by 4 on both sides. If you have a calculator that'll let you shove the whole thing in at once, you could do that. Or else you can do it in pieces and just get the answer to the logarithm first, then plus that answer by 3, get the answer to the log plus the answer by 3, and then once you got that answer, divide the whole thing by 4, and that should work. Okay, what else? Yes, I see. I don't know if I have room for this. On number 14, we have a natural logarithmic equation. Logarithmic equation with the x in a bad spot there, because now we have x's inside the logarithm, and that's hard to solve. So remember, if logarithmic form fails you, you can always just see if exponential form will help. And so let's see here. Remember, a natural log, though, that's a log base e. That's log of base number e of 7x plus 3 equals 3. And so then from there, if we remember that a natural log is log base e, then putting it in exponential form should say e to the 3 equals 7x plus 3. Once we're there, we can just solve this thing out. Get rid of the plus 3, get rid of the 7, and then that'll be calculator work, because now we got 7x equals e to the 3 minus 3 equals 7x. That's supposed to say equals 7x. E to the third minus 3, and then we'll divide by 7, and now we have x equals e to the 3, take away 3, all that divided by 7, and then just shoot it into the calculator and then round it off. It doesn't specify how they want the answer, so you might be able to just type this whole expression right into the answer box if you're careful. But if that don't work, feel free to shoot it into a calculator and probably round it to 4 decimal places, because that's been working otherwise. Let's see here. If I saw these ones, real similar story, so without much explanation, I would say, let's see here, e to the 6x equals 18. That would be like log base e of 18 equals 6x. And then just remember log base e is a natural log, so we could say natural log of 18 equals 6x. And then get that 6 out of there, divide the 6, and then use your calculator as needed. Similar idea on number 16. Let's see. If I had 20 to some weird power equals 17, we'll say that's log base 20 of 17 equals negative x over 15. And then from there, guys, you can run this logarithm just as it is, or else, remember, you can use change of base formula to turn that into a ratio of common logs if you don't get to choose your base. And so that's log 17 over log 20 equals negative x over 15. And then we'll just go to town. Remember, once you get the answer to this mess with the logarithm stuff, to solve for the x, we'd probably times by 15 on both sides. And so times 15 times 15. And then we'll have to just put a negative on it to get rid of the negative from the x, or something like that. So we're looking at, well, I guess if I times by a negative in the first place, like we could times by a negative 15. That would help cancel the negatives here in the first place, just like it canceled the 15s. And so then we'd have negative 15 times log, common log 17. All that divided by common log of 20. And just see how that goes calculator style. Or you can shove the whole expression into the answer box, of course. Let's see here, number 9, very similar idea to what we've done before. So quick take on that one, I would go probably log base e of 44. What? I don't know. That's supposed to say 44. Let's work on that. Log base e of 44 equals 2x plus 1. And then similar idea to all this stuff we've been saying. Remember, that's natural log of 44. And then solve that thing for x. This one looks a little different, but I don't think that it is. It's just weird looking because they're both 4s. And so let's see here. We could say that's a log base 4 of 4 equals x over 2. No big deal. And so what's not real obvious here is that this is probably just a 1. 4 to the something equals 4. But it becomes more obvious when you put it into change of base formula, because then it's just common log 4 over common log 4. They're both the same thing. And so something goes into itself one time, cancels out. Now we just got 1 equals x over 2, and he solved that. Probably get like a 2 for x if he times it out to both sides. Let's see here. What else we got? Find the solution of the exponential equation. Same idea. I would probably, maybe we'll divide the 13 out is the only difference here. If I had, let's see here, yeah. Something like that. If I had 13 e to the x equals 17, I'd probably divide the 13 first to get a weird old thing. Then we got e to the x equals 17 out of 13. And then that's a weird situation to be in. So you start doing the logarithm thing, and you'd be like log base e of 17/13 equals x. And then just remember log base e is a natural log, so that's a natural log of 17/13 equals the x, and then you just shove that into the calculator too. Not bad. Okay, here. This one takes a little bit of thought. We have a computer. What did I do? A computer is purchased for $1,800 and it loses 18% of its value every year. So what I'm thinking here, guys, is this. If we started at $1,800 and it loses 18% of its value every year, it's still keeping most of its value. So let's see here. If we started out with 100%, we took off 18%. What's 100 minus 18? 82, I guess. And so what we're essentially saying is if we lose 18%, we're keeping the other 82%. And so if I wanted to figure out how much it was worth after 1 year, what we could say is, well, I'll take that 1,800 times 82%, or times 0.82, and that would give me how much it's worth after 1 year. And then I'll get some answer for that. And if I wanted to figure out how much it's worth after another year, I'll times that answer, whatever answer I got from this, whatever answer that was, I'll times that by, another 0.82, and that'll give me the new value. And then for the year 3, then we'll take the answer to timesing all of these things, and I'll times that by 0.82, and that'll give me the value at the year 3. I guess all in all, we're just keeping on timesing by 0.82. And so if we were to put this in logarithmic form, we'd say something like this is 1,800, exponential form. This is 1,800 times a bunch of 0.82s, or 0.82 to the x power, or to the t power, where t is like a number of years of time or something. So if they're saying put it in this form, a times b to the t looks like a is our starting point, and then b is the other 82% that we're left with every year, And then they're asking, in how many years will the thing be worth half of its original value? There's different ways of handling this. What I would do is just, here, scribble, I'm going to erase this. What I would do is I would say, well, it started at 1,800, and I'm going to times that by a bunch of 0.82s to some power that I'll have to figure out how many years that goes by. That's the t is time. And I'm supposed to figure out how much time does it take to get to half of its original value. So we'll just notice that half of the original value is half of 1,800. Start at 1,800, divide that jump by 2. Half of that is 900. So then that's what we'll shoot for. We'll say, okay, 1,800 times 0.82 to the t power. I want to know, when does that thing equal 900? And then we'll just start solving. And you can solve it like you've been doing some of the other exponential things, by simply going like, well, I'll divide out the 1,800 here. Divide 1,800, gets that out of the way. And then what that'll do is confirm for us that we're exactly shooting for what they want us to, because 900 divided by 1,800 reduces down to 1 over 2, or a half. And they're asking us how long until it reaches its half of its original value. So it's looking like a half is coming. And then we'll just probably from this point on just go with it in logarithmic form because it's hard to solve it that way in exponent form. And you just be like log base 0.82 of 1/2. Talk about weird notation here. Let's put the parentheses around the half. Log base 0.82 of 1/2 equals t for time. And then you can shoot that into a calculator or use the change of base formula to plug it into a calculator as well. So it's common log of 1/2 over common log of 0.82. And then that's calculator work there. Some number of years, you know. And then slide 12 is an accident, so that's good. You guys are doing good. Pause recording, stop recording, there it is.